Good afternoon, everyone. So we're going to reconvene right now. And to wrap up this morning's session, we're going to have the last talk of the session, but the first talk of the afternoon by Anna Grau-Gallofre, who's going to talk about interrogating the origin of Casei-Valles from flow to form.
Yeah, thank you. Thank you very much for the introduction. Yep, and thanks for the name pronunciation. I know it's not an obvious one. So I'm a bit of an outlier here. I'm going to be talking about flow channels, and I'm going to be talking about geomorphology and flow dynamics. And I think I'm the only person actually talking about the flow channel, so let's go. So most of you are Martians, so there's not much point in comparing the terrestrial and Martian timelines, but you know, like a lot of the talks we've seen so far are kind of like painting this picture, and we're looking into Pre-Noachian, Noachian, Hesperian, Amazonian, and essentially the long-term evolution of the climate. So we are moving from a habitable climate with the presence of valley networks on the surface. Whether or not there was an ocean on Mars, it's obviously up for debate. And then as we move further down into the Amazonian, there's a more and more consensus that we're moving into a cryospheric world in which the mobility of ice deposits essentially changes depending on the obliquity configuration. So somewhere around the time where we start to see this transition into global cryosphere is when we start to have the development and the formation of these outflow channels. Some started earlier in the Noachian, a lot of the activity happens in the Hesperian, and some of them are still active later in the Amazonian period. So this is Casei-Valles as an example, and these are the circumcretia outflow channels. And what's interesting about those outflow channels is that they're big. They're the largest erosive structures in the solar system, and that means that they're both source from and sustain vast water reservoirs, and they're able, most importantly, to mobilize massive water fluxes. And as such, obviously, they're very important elements to any understanding of the long-term evolution of the hydrological cycle and the climate. There are several hypotheses of formation that have been argued over the years. So, of course, the predominant one is the megaflood hypothesis, which was proposed by Milton and Baker in the 1974 paper, and then followed up by many multiple papers. But I also like to draw your attention to two other hypotheses that have been suggested for the origin of these mega canyons, which is ice streaming, suggested by Barbel Lukita in the 80s and followed that in the 2000s, and then the lava flood hypothesis suggested by Leverrington. But focusing now on the mega flood hypothesis, essentially, this hypothesis was raised on comparisons, analog comparison to the channel scablands, which is this landscape I'm showing here in the southeast of Washington state in the US. So this landscape formed during the multiple collapses of glacial lake Missoula, like repeatedly during the Quaternary. And during the collapse of this glacial dammed lake, essentially a lot of water, like massive volumes of water were essentially released at the same time, mobilized, as shown in this figure here, and eventually released on into the Pacific Ocean. And what's interesting here is essentially the characteristic landforms that are formed related with high turbulence, and then this is shown in the figure on the right by Big Baker in 2009 in this retrospective. So a lot of what drives the erosion of this landscape is going to be the extremely high level of turbulence that we find associated with this mega flood, with this collapse of the aquifer. However, this mega flood hypothesis to explain the outflow channels comes with a couple of rather important shortcomings. And I'll add a third one perhaps later. So first, talking about Casei-Valles, so for example, the scale of Casei-Valles and the lack of meaningful analogs. So Casei-Valles is 2,500 kilometers long by 300 kilometers wide and by kilometers deep. In comparison, the channel scablands, which I was showing here, so there's no scale here, but it's around, yeah, there's a scale. So that the scale there is 40 kilometers, right? And the whole thing is no much more than 250 kilometers. So it's much smaller, it's another magnitude smaller than Casei-Valles, and each of the individual tracks are much, much smaller. The other one is the idea of the source of this mega flood, essentially the collapse of a subsurface aquifer that could have been driven by some cryospheric overload or essentially, different processes have been proposed. But essentially, the important thing is we're releasing massive amounts of water in very short periods of time. And the problem to do that is that you require very high permeabilities to do so. And the high permeabilities that you require are about 7 orders of magnitude higher than what's actually observed. And that's a lot. And the third problem that I didn't drop here is going to essentially, how do we recharge this aquifer? We can essentially activate a megaflood perhaps once or twice, but it's actually very hard to recharge these massive volumes of water. And activity in the outflow channels has happened several times throughout Mars history. So these are the 3 problems with the megahot hypothesis. And I'm sure some of you are already looking at the table down at the right, and that's hinting at what's coming next. And essentially, it's this concept of equifinality in geomorphology. There's a lot of landforms that by themselves are not always uniquely related to a specific problem. And in this particular case, there is examples of landforms that I'm listing here, and there's some other more. So bedrock incision, the presence of longitudinal grooves, cataracts, the presence of hanging valleys, inner channels, streamline islands, U-shaped valleys, confluent zones. All of these are seen both in megaflood and ice stream examples. So what's an ice stream, you may wonder? An ice stream is essentially like a fast-flowing megaglacier. We're looking at speeds of kilometers per year and widths that are closer to the hundreds of kilometers, tens of hundreds of kilometers, and hundreds of kilometers length. So that's an ice stream. So essentially what this is suggesting, and this was first pointed out by Lukita, is that these different landform assemblages that we see inside of the outflow channels could also be indicative of ice streaming behavior. Right, so the question this begs is like, okay, so like back at the time in the 70s, outflow channels were interpreted to be sculled by megafloods. However, the geological record of ice streams was not actually understood until the 2000s. And at that point, there was already a well-established interpretation in place for outflow channels that was then not necessarily revisited later on. So the idea of this project that Nicola over there is going to start working on as in his PhD is to actually revisit this idea starting from fluid dynamics, so looking at the bed forms inside of the outflow channels and backpedaling from bed forms, Reynolds number, state of turbulence, from the state of turbulence linked to the other bed form and the morphology, and from that coming back down finally into the climate environmental implications of that. So a landform that has been suggested several times to be invocative of liquid water and of flooding events are streamline islands. But streamline islands are actually just the result of, this is the shape that essentially minimizes drag, and they're actually seen in like a lot of different fluids, right? So it's not a landform that it's specifically telling us that there was water, and it's not a landform that's specifically telling us that there was a flood. These examples are showing lava streamline islands and ice streamline islands, and at the bottom right, of course, those are megaflood streamline islands, right? And this is a streamline Ferrari. So it's really this idea that it's the shape that minimizes the drag, right? So once again, equifinality. One landform is not necessarily conducive to one given hypothesis in geomorphology. So what's interesting is to start looking at the streamline island. So here's a really nice example that we see, and to try to derive what is the dynamics of the fluid that made this, right? So is this, we're looking here, for example, on this diagram here, we're looking at the drag versus the Reynolds number of different obstacles of different shapes, and we see that the streamline shape is just the shape that happens to minimize the drag, right? But the interesting thing here is that we can take the shape of the streamline objects and we can actually track what type of flow regime was at the cause of that shape, right? And in some instances, we can even extract that from the geological record. So in this case, for example, turbulent flood is not consistent with what we see in the geology of this particular bed form, and we do require viscous flow to explain this streamline form, right? So we can obviously do that across all of the streamline islands where we do see evidence for what the flow was doing around. So this is not always the case. Like here's another streamline island that shows possible bone-Kármán vortexes, and in this case, this would actually be conclusive of flooding and high turbulence and high Reynolds number. So the idea is going to be like looking at the different bed forms found inside of the outflow channels and extract that information, and then map it out across of the different outflow channels to know if we're looking at floods versus megaglaciers. Once we know that, we're going to be revisiting the idea of whether megafloats or megaglaciers are at the origin of this. So at the top part, this is an image of Kasai valleys. In the middle part, this is the northeast Greenland ice stream. And on the right, these are the Missoula megafloats as seen on the landscape. And I invite you to look at the different spatial scales and the different form and the morphology of these different objects. And in the bottom row, this is essentially looking at the morphology of the bed that we find in Kasai valleys in an ice stream. So this is an ice stream bed from the Laurentide ice sheet in Canada. And on the right, this is the groups that are exposed in the channel scablands. So once again, pointing out the fact that those groups are not necessarily unique and not necessarily related to flooding, that other landforms and other processes can be occurring. So we're going to be characterizing the morphometry and the morphology of individual bed forms and the continuum of bed forms inside of the outflow channels, and interrogating what, in this case, for example, spectral characteristics, which I'm showing on the right, are most consistent with one or the other. And the last thing to do is going to be looking at the morphology. So the top are examples from Martian outflow channels, and the bottom are examples from terrestrial ice streams. So we can see a lot of landforms, and notably on the right, we can see water landforms that have been incised on the grooved bedrock that we can see at the base of the outflow channels on Mars, right? We're going to be comparing the morphology of ice streams and following the criteria to see if the morphology is consistent or not with what we see in the outflow channels. All right, so coming to some conclusions so far, and these are preliminary results that we're working into a paper. Fluid dynamic observations require glacial flow in some areas inside of the outflow channels. But are these areas representative, and how much erosion? And how big was this ice body, and how much do we require for it? Results also confirm turbulent flow. So that means that it's a lot more complicated than just megafloods or megaglaciers. There's probably a little bit of both, which is usually what happens when we look at the Martian landscape. It's always more complicated than what we expect at the beginning. And the idea is going to be looking at the distribution of the different observations and to mapping that into the different outflow channels to come back to a broad environmental conclusions. So this is a project that's starting now. So I'm taking the chance to advertise that. I'm going to be looking for a PhD student to start next fall and 2 postdocs to be starting in 2026 and 2027. So if you're interested and you're in that stage of that career, please send me an email. Let's chat. Yeah, take the chance to advertise some more. Thank you.
Thank you, Anna. Question for Anna? Please go ahead.
Bethany Elman, Caltech. Number one, I am so glad that you're studying the outflow channels, as I think they're one of the most understudied features on Mars these days and are still mysterious. I wanted to just say one thing as a slight caution, but then also ask a question. The slight caution is that I think it's super important with some of these streamlined forms and also like the shape of and the volume of the valleys to remember that there have been about 2 to 3 billion years of wind erosion since then that have created, all kinds of other features on the landscape and sculpted it. That's just a comment in terms of using the modern day surface. But the question is actually, I wonder if as part of your work as well, you'll revisit the question of the source of water. I think at the time of some of the outflow channels, there was this assumption it was coming out of the subsurface. And I agree with you very much about the permeability problem. But on Earth, of course, it was actually surface ice sheets and surface lakes that were dammed by ice sheets. And so I wonder if there's also some way to kind of reconcile these end members into a system. Maybe you can comment.
Sure. So in terrestrial environments, ice streams are very often found linked with megaflooding. They come hand in hand quite often, actually. And the thing about the glacial imprint and outflow channels is that it greatly facilitates both the source and the fate of the water. So you don't need to invoke the difference in permeabilities, and you don't need to worry about how do you recharge the aquifer, because the aquifer is just the ice body. Whether you're looking at a lake that is ice dammed, or you're looking at essentially ice stream at the bottom of the ice sheet. Is that something that we're going to find out as we interrogate a bit more carefully the fluid dynamics? And you pointed at wind, and wind is fun because it stays, at the other end member. It's still a highly turbulent fluid. So we should still be able to pick up ice from wind. The nice thing about ice is that it's extremely viscous. So hopefully, yeah.
Yeah, I think it's just the wind could have overprinted some of the ice stuff in the meantime. So, but I look forward to the results.
Yeah, thank you.
Jim Head, Brown University. Excellent talk, and I'm glad you agree with Bethany. I'm glad you're working on this problem. I would also encourage you to think about a hybrid model, kind of like what Bethany was talking about. James Casanelli and I did a couple papers looking at volcano-ice interactions. Tharsis in this era is likely to be a cold spot and cold trap, and the volcanoes are still going to be pumping away. So I'm sure you've thought of this, but consider a volcano ice source for the water, but then it returns immediately to the glacial stage, and you can get some late stage glacial modification and streaming. So perhaps a hybrid model.
Yeah, absolutely. And once again, as I said before to Bethany, usually ice streaming and mega floods come hand in hand. And the nice thing is that you do have a heat source, at least for Kasai. The other flood channels, not so much, but Kasai seems like may facilitate. Yeah.
Right, do we have another question? We still have some time. Well, I do have a quick question. Does it, in the case where it was indeed carved by ice flow, does it put any constraints on the climatic conditions that we would need to accumulate enough ice to create this flow at this location?
So yes, I mean, you need a minimum volume of ice, and from the ice direction, you can backpedal into what the expected geometry you can expect from that ice. So I think putting constraints on the flux and the volume are things we would be able to do. But I mean, it's still really early on, and that's going to be a question for Nicolas, my student, later on. But we do expect to be able to constrain volume and fluxes.
Yeah.
To comment on that, I will think, like shown by Frederick Schmidt, for instance, I think it's important to have high pressure enough so that you start to have gradient in temperature with the vertical. Right now on Mars we don't have that, and we put a chart actually of the temperature gradient with topography as a function of pressure in our paper in 2013, and I think it probably requires minimum pressure to have that. Otherwise, there is no reason to have glacier there, or it has to be very.
Yeah, absolutely.
Right. Well, let's thank our speaker again. And we'll now start a new session on Mars redox through time. And Adomas Valentinas is going to kickstart this session speaking about unlocking early Mars redox conditions, evidence from planetary scale iron oxide deposits.
Okay, hi everyone. I'll present some of the work I've been doing at Brown University and also at ETH Zurich. So let's get into it. First of all, what is redox? So redox is basically a chemical reaction that happens that releases energy. And one example is if you look at your flashlight, you put in a battery, right? And at the negative terminal, you have zinc that's being oxidized, so it's losing electrons, and then those electrons are traveling to the positive terminal where you have magnesium dioxide. And this travel of electrons releases energy, and actually, in some ways, you and me now, we're breathing, right? So redox chemistry is happening right now because as you're inhaling oxygen, oxygen is being used to oxidize glucose, and glucose then can be used, the energy produced in mitochondria can be used to drive biological activity. So there are abiotic and biotic processes that use redox reactions, and they're quite important for Mars as well. So if you look at the solar system, Mars is quite special. So the surface of Mars is red, and a lot of the early research in the Viking era was driven by this question, why Mars is red. So what I'm doing here is basically I'm reinvestigating this old problem with fresh insights. because the redox processes are important. They happen in the Martian atmosphere, on the Martian surface, and also in the ancient, could have happened also in ancient Mars waters. So it's an important problem that we should address and try to investigate. So I'm basically tackling the Mars redox problem through iron mineralogy. So I decided to synthesize and acquire many different natural and synthetic iron oxide, hydroxide minerals. And I was doing mixtures with basalt and doing visible near-infrared spectra of these powders in the lab. I was also doing X-ray diffraction analysis for mineralogy, as well as some dehydration experiments and kinetic calculations, which I will recap really quickly because this was published already in February this year. But I feel like it's important, a lot of these results are important, and I've not shown them before to the community. So I think it's good to recap this quickly. Also, what's interesting is that we also found that in the Martian dust there may be up to 30% by weight ferrohydrate, so it's not 1 or 2%, it's actually quite significant. So let's go quickly into the results. So this is visible near-infrared spectra of my ferrohydrate basalt mixtures, seen in blue, and then the other spectra are from the rovers and the spacecraft. So you have Mars exploration rovers and the IMP rover spectra that's shown in the data points, and the lines are spectra from the orbiters. There's also one spectra from ChemCam MSO is shown in cyan, that's from Johnson et al. So these are spectra acquired from already established literature and published papers. So you can see that the fit is extremely good. Now if we compare this to mixtures of basalt powder to other iron hydroxides, you can see that the electronic transition absorptions are quite distinct for other phases. And ferrohydrate is the only mixture that provides a good fit to the Martian spectra. Also, what's interesting is that our powders were hyperfine because we're trying to simulate the actual particle size distributions of the Martian dust, which is everywhere on the surface, as you saw in the previous image. And it's, it's quite prevalent, and it's been lifted up by winds and the dust storms and distributed over the surface. So we had these powders below 1 micron in size, actually. So there was this question about, okay, so is ferrohydrate stable on the surface of Mars in the present day? What we did is we exposed these powders to ultraviolet radiation and also low pressure, so 5 to 6 millibars pressure, so present day surface conditions of Mars. And what we saw by acquiring X-ray diffraction patterns, as you can see here, before and after, so this is the same powder measured before and after the dehydration experiment, we are not seeing any change in crystallinity, so which suggests that ferrohydrate is perfectly stable thermodynamically on the surface of Mars. Well, you might say that, okay, so this is 30 days experiment. What about billions of years of Martian dehydration? So we addressed that as well. So we employed kinetic calculations, and also there are strong theoretical reasons why ferrohydrate would remain stable under cold conditions. It's basically a transformation kinetics are controlled by temperature and by iron self-diffusion. So basically at 210 Kelvin, so minus 60 average temperature on a Martian surface, ferrohydrate is basically thermodynamically locked, and it's the transformation to goethite, for example, under those conditions would take billions of years. Actually, if you look at Arrhenius law and you use reaction rate constants published in the literature, you can end up with times that exceed the age of the solar system, so and actually of the universe. So basically, the theory strongly supports the idea that ferrohydrate under cold and dry conditions is just stable on the Martian surface. Okay, so then the question is ferrohydrate modern or an ancient weathering product? And If it's an ancient one, how old is it? We favored the ancient hypothesis because to form ferrihydrite, you need liquid water to mobilize the iron, and because it's the Martian dust contains a lot of ferrihydrite, you probably need a large, somewhat significant amounts of water, which also is in line with the recent work by Luju, who has published this paper on Medusa fossae formation and suggested that the vast amount of the Martian dust is being eroded from Medusa fossae formation and then being distributed over the Martian surface. So his work suggests that if you eroded the entire Medusa fossae formation, you would end up with a global equivalent layer of 10 meters of dust. So it's definitely a significant amount. And since I made this connection between the Martian dust, its hydration, and ferrihydrite, you can then evoke this idea that perhaps you needed, not only there was a lot of liquid water that was needed to form this ferrihydrite, because if you chemically weather basaltic materials, volcanic materials with water, you end up having ferrihydrite. But also the next thing is the oxidation. So how this iron was oxidized from Fe2 plus to Fe3 plus. And I'll come back to this in a couple of slides. But let's first also maybe talk about the results from the FRIEND instrument. So it's FRIEND is an instrument on trace gas orbiter. It's an epithermal neutron detector, which basically shows you here that the bright and dusty regions on Mars, they contain also elevated hydrogen signature, which actually is not that of a shocking result, because we knew this since 2001, since Mars Odyssey results and its gamma ray spectrometer investigations. And here I'm just showing you that these regions shown in black boxes, this is where Medusa fossae formation is. So on the left and the right side, center is Arabia Terra, which is also includes elevated hydrogen signal. And I'm here also plotting the distribution of clay minerals as far as we know. What is interesting is that there seems to be somewhat an anti-correlation between the observed clay distributions and the elevated hydrogen abundances in the dusty regions. So what I'm saying is that perhaps these elevated hydrogen signatures can be linked to perhaps ferrihydrite-rich dust tones. Okay, so I still see I have a few minutes, which is good. So what is the nature of the oxidant? So here are just preliminary investigations and the results from the lab, where I'm synthesizing different types of iron hydroxides. So basically what I'm trying to do is I'm trying to use the mineralogy to constrain the surface environment on ancient Mars. And each different oxidant leads to a different iron hydroxide mineral. So the mineralogy can actually provide very strong constraints on the surface oxidizing conditions. And here you have just snapshots. You can see in the middle magnetite. So it's iron oxide mineral that has no water, but it's magnetic. And you can see that it's, the crystals are following the magnetic field line. So it's kind of, because in my fingers I'm holding a magnetic stirrer. So you can see that the magnetite is really magnetic. And then below it you see a plate of ferrihydrite, so it's freshly precipitated in the solution. And then on the right side you see green rust solution, so this is Fe2 plus rich aqueous solution of iron. And if you look closely you can see the bubbles, and this orange deposit on the glass vial is where iron is being, as we, in this picture, is being oxidized just by air, by the oxygen in the air. And I did collect some of the sample to look at the mineralogy, and it was a lepidochrosite. So right now, I'm getting all these different phases. I also get ferroxyhide. So there was a nice presentation yesterday about ancient hydrogen peroxide in the Martian atmosphere. And basically, what in my work shows is that if hydrogen peroxide was abundant in the atmosphere and then in the surface waters, you would have expected to form ferroxide, but ferroxide is not observed on Mars, and it's not in large amounts and large abundances in the Martian dust, in contrast to ferrohydrite. So this is still ongoing work, and I'm trying to basically form ferrohydrate and understand the ancient climate. So in conclusion, I hope I convince you that ferrohydrate is a powerful indicator of the Martian water history and redox processes. There is up to 30% ferrohydrate in the dust, and this suggests that the weathering process, the chemical weathering process that formed ferrohydrate is important. It also probably must have formed long ago when liquid water was present in significant amounts and when the surface was oxidizing. So now the question is, I know that if someone of you read the abstract, I said that we'll propose and show in the conference a redox model for Mars through time. But this is TBD, and the question is, was it reducing as most of the models suggest, and then oxidizing, or maybe it was oxidizing in the very beginning and just the redox power waned over time? That's still up to debate and up for us to try to resolve in our experiments. And so with this, I will thank you and take questions.
Questions for Anomas? Yes, please.
Hi, Erwin Oak, University of Lyon. Very, very nice work. I was wondering, on your experiments, are you planning to test other parameters than the nature of the oxidant? I'm thinking in particular of things like the water-to-rock ratio and the pH of the solution. There's a bunch of work in the literature that shows that there's an influence on the nature of the oxides that precipitate.
Yes, yeah, oh, sorry. Yeah, we're definitely we'll try to address that and investigate, because pH is definitely an important factor in this, and we also want to use a Mars chamber, or at least some sort of environmental chamber where we can change the atmospheric composition, because right now, the experiments are really initial kind of tests where I was doing it under ambient conditions. So we're, there's a lot of room to expand and improve on. Yeah.
Hi, Frederick Schwinn from Geoscience Bicycle. Very nice work. As you know, spectral identification of minerals is always a very hard task. And I was wondering if you try to change the grain size, because it makes change the shape of the band, and what is the effect of that?
Yes, so this is an important and true point. So we did, as I mentioned, we did the hyperfine particle size mixtures. So we were grinding actually our ferrohydrite and basalt with colleagues at Grenoble, with Pierre Beck, and it does have an effect. And we actually did notice that having hyperfine particle sizes, it fits much better with the Martian dust spectrum. So, so it does have an effect, and we did see that small particles are actually a better fit to the spectrum. Yeah.
Do we have another question? If not, let's thank Thomas again. And we'll now move on to Yuyan Zhao, who's going to present about the evolution of iron redox on Mars from iron-rich crust to ferric dust.
Good morning, good afternoon. I'm Sarah Zhao from Chengdu University of Technology. And during the past years, my students and I are focusing on the iron redox study on the Martian surface. And here I list all my students with a plus sign on their names, who leading individual papers, and also acknowledge my collaborators to make this series of experiments possible. So we now know that Mars is a red planet, and we have identified various secondary ferric minerals on the Martian surface. So one of the key questions that we are asking is how and when did the Martian surface begin to oxidize? And do we need a planetary scale like oxidation events, great oxidation events that happen on Mars to produce that we have seen today? And also because we have, during the past decades, we didn't really see much of the organic or microbial activities on the Martian surface, so we really lack of the reduction process for Mars. So is there any way that we can reduce the Martian surface a little bit? So that's the key question that we want to answer. And one of the fundamental difference between Earth and Mars is that the Martian crust is really iron-rich. So we have identified a lot of iron-rich olivine on the Martian surface. And comparing to that, the most thing we're familiar with the olivine on Earth is that is mostly like the forsterite or San Carlos olivine. And another thing is that Mars, because it's very iron-rich, so the iron is actually the key to control the water, rock, and the salt system on the Martian surface. So the behavior of iron is very important for understanding the evolution of the Martian surface. So our strategy is to design a series of experiments to constrain that the acknowledged gap that we're missing, based on our experience. So for the Noachian, we focus on the alteration of iron-rich olivine, and for Hesperian, we're trying to see how the iron 2+, 3+ sulfate evolution and the sulfate halogen interaction. And for the Amazonian, because we know that it's very oxidizing, and we really want to see how the water acts as during the processes. So here as the major finding that we have is that if we have aqueous or icy alteration of iron-rich, we actually see the preferential leaching of magnesium, and we see the iron is really readily oxidized by water even under anosic conditions. So this is the powders that we synthesize for the experiments, and we also have the San Carlos and the forsterite for control for comparison. So the first thing we do is because we know that spherical weathering on Mars, and we want to see that under cryogenic conditions, what will happen. And consistent with our understanding that we found that iron is primarily in form of iron 2+ and highly mobile with a very high acidity. And one thing is, out of our expectation, is that we usually think magnesium and iron will release just stoichiometrically. But we can see that for the iron 70, the Fa71, you see the iron is actually, the ratio is actually lower than we expected. So the iron leaching is kind of hindering even under the very acidic condition. And we'll also try another experiments that under 1 bar carbon dioxide atmosphere, and for this one we don't have any oxygen in the system. And we actually see that the magnesium is preferentially leaching into the solution, which means that on the rim of your olivine grain, you will have higher Fe number on the rim, and comparing to the initial olivine. And the iron retain mostly in the secondary amorphous silicate that will to be the precursor. We think they will be the precursor for the iron ferrous saponite. And we'll also try another scenario that because the icy highland, and maybe we will have some of the ash and the ice, they are compact and have under high pressure, and what will happen to the olivine. And we designed this experiment, and we see that unexpectedly, even on the very anasic condition, we find iron 3+ phases are commonly present in our products. We found the nanoscale spheric iron oxide particles, as you can see in this picture. And also we can identify the ferrocapipide and the jarosite produced in our experiments. So for that, we can see that under the ambient condition or the cryogenic condition, you will easily oxidize the iron 3+ under the iron-rich olivine. And another thing is about the serpentinization, because we are very familiar with the phosphorite or calcium colors serpentinization, but we don't really know that under the even under argon gas, what will happen for the serpentinization if we have the iron-rich olivine as the initial material. And so to our surprise that we found actually if you have a phyllite or very iron-rich inner member, you will actually produce the products, altered olivine, and you will also have a solution with a very dark color. So that is the iron 3+ in the solution. So consistent with our observation, we find that we have, with a very high concentration, the phyllite in our initial material, you will actually produce a very high concentration of iron, magnesium, and silica in the solution, and the very high solubility, solution fract will happen in these experiments. And for the products of the altered olivine products, as the St. Carlos, we have the brucite, the magnesium serpentine, and the no tag or magnetite observed as we expected for the very early stage of serpentinization of phosphorite. But for all the iron-rich olivine, we find no brucite in solution, and also we find magnetite and the tag and the minnesotacite solid condition solution in the system. And also we can identify the ferrous-bearing, the iron-bearing 17 in the Fa30 experiments, and most other experiments we found the iron 17, the cross-statite, as the major production. And to our surprise, even we see those 3+ in our system, in our products, the altered olivine, we don't really see much of the 3+. So based on the Mossbauer experiment, Mossbauer analyze, we estimate the 3+ is just below 2 or 3%. But in the solution is another story. We froze dry the precipitates, and we found that by Mossbauer, more than 30% of the products are 3+. And we found they predominantly cross-statite. And we can see that on the right picture, the magnetite with the nanoscale grow on their surface, on the serpentine surface. And the synchrotron analyze also consistent with our analyze that we have our oxidized iron, and we also find the fingerprint of cross-statite. So what that means is that if you have iron-rich olivine with the serpentinization, you actually will produce a solution with high concentration of iron, magnesium, and silicon, and you don't really necessary to see the altered olivine with high abundance of serpentine mixed in with it. And with those solutions, it can be very highly mobile, but they contribute to the 3+ to the aqueous system on the Martian surface. And based on our experiment that we observe in the Fa50, that we think that represents the average of the Martian crust, we estimate that for 1 kilogram Martian crust to dissolve, involved in the serpentinization, we will actually produce about 60 millimole of hydrogen in this experiment. So for this one, we actually see a lot of a very high fraction of altered olivine involved in serpentinization and the hydrogen production. And another finding about the impact is that how the impact will induce the iron redox cycling. Because we know that in early Mars, there should be a lot of impacts on the surface. And the previous study have indicated that if you get impact and then they got to remelting, you may increase the oxygen fugacity. And also if you have water involved in the system, you might generate hydrogen with oxidized the crust. But what about if we don't have water in it? So we tried the shock recovery experiment on the Fe50, which represents the average Martian crust. And we actually can form a lot of nanophase metallic iron particles in our olivine. And we also find that the iron can migrate outwards the olivine grain, and we will also form some of the magnetite, which on the rim of the different particles, suggesting that they might form by the impacting to oxygen and the metallic iron particles. And another two observations that we thought they might be interesting to Mars is that we will maybe have the iron-rich olivine, they are secondary, produced by the impacting events. One thing is that when we do the shock recovery experiments on the phyllosilicate with a very high speed impact, we actually, from the remelt, we form submicron olivine crystals in our products. And another one is for the new founding gabbroic shergotite. It's very high shock level, and we actually see the phyllite. It's very iron-rich, so the phyllite appear to be fractured fragments on the rim of well-crystalline pyroxene, so we think they are secondary. So these are they bring the new story about maybe the phyllite olivine. They're not only magmatic, they can form by the impact. Another thing is for the Hesberian, it's very important. They might be very acidic, or they might be acidic, and they might be freezing, and they can also, the sulfate and the hydrogen, the interaction may be the key to controlling the surface. So one of the experiments we're working to see that under the UV radiation, even with a very high acidic and the iron sulfate brines, you can still efficiently to oxidize the 2+ to 3+. So you will forming a lot of ferric sulfate with amorphous materials. And those sulfate materials have really important indications for the halogen redox processes. So one of our experiments to see that, because the perchlorate and chlorate are very important for Mars, because perchlorate is actually active to involve in the redox processes. And we found that with the ferrous sulfate, you will form more perchlorate than chlorate. But with the iron oxide, you will have a lot of chlorate forming than the perchlorate. But another interesting observation that we made on the right is that if you're mixing the perchlorate sulfate and under the UV radiation, they actually protects the perchlorate from photodecomposition, and that won't happen to any other sulfates. And we think they might be very interesting characteristics related to the ferric sulfates. And another thing relevant to the halogen redox is that we know that bromate is very active, and they can redox, interact with the magnesium and the iron. And our experiment with the freezing condition also show that the bromate redox can also effectively oxidize magnesium and iron even under the -80 Celsius degree. And the final findings is about the critical roles of water. So we now know that Mars is very oxidizing, and we have identified a lot of oxidants on the Martian surface. So our experiment comparing the halogen oxidation experiments under the photochemical conditions, we found that if you don't have water and oxygen in your system, actually you don't really have the source of oxygen for the oxychlorine species to produce. So comparing the Martian condition and the lunar condition we are working, we find that if you under the lunar condition, like no water, no oxygen, you actually have very low yields of the perchlorate or chlorate on the Martian surface. So which suggests that water is actually the key for the Martian surface. So the summary is that based on our experiments, we found that the iron-rich Martian crust is more readily oxidized than traditionally recognized, and we are expecting the very early in the history the Martian will start to show the sign of the iron 3+, and also water plays a very important way during the processes. And with that, because we have coupled iron, magnesium, chlorine, and bromine, the redox system on the Mars, so we don't really actually need the atmosphere oxygen molecules to produce what we have on Mars today. So that's all. Thank you very much.
for the speaker, yeah, Alomas, go ahead.
Adam Valentinas, ETH Zurich. First of all, thanks a lot for the work. We need more work like this in the community, I believe. Yeah, you did briefly mention the moon, and probably I'm sure you know of this hematite detection in lunar poles. So what is your kind of intuition telling you about the formation of hematite in the poles, for example?
Okay, so I don't really know that very much because that some of my colleagues are working on that. But our focus is on the chlorine on the lunar surface. So we're working on starting with the halite to see how much of the halite can convert to the oxychlorine species. But I don't. Yeah, I think for the hematite maybe on the moon, maybe you also need some kind of source of oxygen to contribute to forming the compound.
Thank you.
Hi, Matteo Losch, IRAP. Great talk. And yeah, congrats for all these experiments. I don't even imagine the work behind. And yeah, my question is a bit naive, but we say that Mars is oxidized, but we speak just about the surface of Mars, right? And I think, maybe you can correct me, but most of the processes you show result in kind of low weathering rate, in the sense you do produce oxides, but not in large quantities. So I understand when we imply all these processes for explaining, for example, the surface dust, but in terms of mass of rock, as soon as you drill, is going to be reduced, right, on Mars.
Sorry, would you repeat?
The question basically is here all these processes, you use them to explain the surface dust. But for example, I'm thinking about like some stuff we saw with the Curiosity rovers or other formation, for example, in Gale Crater, where you have a lot of, like most of the rock is oxidized, but the bedrock itself, not just dust, basically. So would that work also for this kind of observation, or is this just to explain low weathering rate and production of iron oxide, but low amount, basically, that are distributed around the planet?
Oh, yes. So, so for the design of the experiments, we mainly like simplify like some of the conceptual model to see what the pathways might work. Some might not. So one important thing is to connect those experiments to the in situ observation or the orbital observations and also we know the geological process is very complicated. So so there's a lot of work to combine them together.
Yeah, I just to make my question clearer is also because, for example, when you were speaking about the acidic oxidation, we also know it's a very, very low water-rock ratio, which implies also you're going to make a very oxidized layer, but the whole rock will be still reduced, basically.
Actually, depending on the specific geological settings. Yeah, so for Mars, we can see the surface dust are really oxidizing, but actually in the bedrock, you don't see much.
Yeah, exactly.
Yeah, you don't see much of that. So that back to the that might back to the assumption that we have a lot of water and the alteration on Mars. I think that might suggest that the water is really limited or the interaction are limited. Otherwise, it should be very easy to see a lot of oxidizing signs. That's what we understanding right now.
Also, maybe I did not understand. Have you tried some atmosphere rock interaction, like moisty atmosphere?
Moisture of the atmosphere.
Like exposing a rock or a powder to an atmosphere?
Not yet. So our experiments we want to keep it on an anosmic condition, so maybe carbon dioxide or argon, nitrogen, things like that. Yeah, but we don't really expose them. And now some experiments we're working on the metal stable phases, like the ferric sulfate and oxides to expose them to certain conditions to see how if they will transform or not. But that's another work. Thank you.
Great talk.
Right, thank you. We'll have to move on. Let's thank our speaker again. Now, to conclude this discussion on redox, and before moving on to the atmospheres, we'll have an exceptionally online talk. For visa reason, our speaker was not able to join, but thanks to the high tech we have here, he'll be able to give his talk. So the speaker is Jiasheng Liu. Jiasheng, are you with us? Maybe.
Sharing.
Oh, we see you.
Doesn't hear.
We don't hear you for the moment. Do you hear us? Just give it a minute. That's gonna work.
Je vais passer sur le micro ici. Ok, je vais faire un truc là. Je passe comme ça, hop. Hi, Jiasheng, can you hear me? Can you hear us? Oh, too bad. Jiasheng, sorry, can you hear us? Yeah, sorry, we could not hear you. I think you were going to resume with the sound here. Go ahead. Sorry, we have to start from scratch. I'm sorry we could not hear you from the beginning. From the beginning, yes. Can you hear in the room?
Yeah, I can hear. Can you hear me?
Sélectionner Scarlett en fait.
On l'a déjà fait, ça marche pas.
Si,
Just a
ça
second.
marche.
On va après faire,
Ah,
alors.
si,
Allons-y,
si,
parfait.
Si, ça marche.
On prend Scarlett, voilà. Can you speak? Je couperai le micro s'il y a de l'écho. Can you hear us? Done? Can you hear us, Jiasheng? We can't hear you, but maybe if you show a thumb up, we'll know if we can hear. can you try to speak again? If you can hear us? Okay, sur le son. Sorry, Ashin, can you speak again? Maybe we can hear you now.
Works?
Let's do that.
Yeah, perfect, yeah. So I hope you can hear me clearly now. This is Jiacheng Liu from the University of Hong Kong. My work is about climate transition and atmospheric redox evolution of early Mars revealed by surface iron mobility. So the basic scientific question is when and how Mars become cold and bipolar. So we know early Mars characterized by icy highlands, but the present Mars has bipolar ice caps. So the key question is when and how Mars become cold and bipolar, and when did Mars surface get oxidized, and was the climate transition coupled with the redox evolution? Martian climate and redox evolution could have been well recorded by surface composition, including hydrous minerals and geochemistry. Hydrous mineral evolves from clay minerals, surface, and iron oxide or hydroxide. For geochemistry is another very important aspect. We know iron mobility can be affected by a redox by temperature and acidity. So the distribution of iron can be used to reconstruct Mars' redox state and the temperature. Widespread surface clay minerals indicate a warm climate on early Mars, at least episodically. However, it's not easy to warm early Mars because early Mars only receives 13% of solar radiation. Long CO2 greenhouse was required to warm early Mars. The most plausible mechanism for long CO2 greenhouse, including reducing greenhouse and the ice cloud radiative effect. Basically, I'm going to focus on the reducing greenhouse mechanisms. Basically, for the mechanism, it requires a percentage level hydrogen and and 1 bar or 2 bar CO2. For hydrogen, there are multiple sources of hydrogen on early Mars, such as volcanism, subplanetization, and impacting. And the intensity of the hydrogen gas, the reducing the intensity of reducing greenhouse is positively related to the concentration of hydrogen. Theoretically, the loss of hydrogen or the oxidation of atmosphere would result in climate cooling with time. So the reducing greenhouse warming also lead 1 bar or 2 bar CO2, under such high pressure conditions, it can cause strong adiabatic cooling. Temperature decrease with elevation. Recent work shows that the greenhouse can also produce strong adiabatic cooling. On early Mars, there are both strong greenhouse and pretty high atmospheric pressure. Therefore, there should be a pretty strong adiabatic cooling. The temperature is pretty low in highland region. The low temperature can accumulate abundant water vapor to form the water ice in highland, to form the icy highlands. So I'm going to use iron mobility to test the reducing warming mechanism. I use the iron mobility as a redox proxy because iron 2+ is soluble and mobile under chemically reducing conditions, but iron 3+ is insoluble and less mobile under oxidizing conditions. For example, on early Earth, there is strong iron loss from paleosols happened under a chemically reducing atmosphere on ancient Earth before the Great Oxidation event. Can we find similar phenomena on Mars? Yes, we have found strong iron leaching. I have found strong iron leaching from chemical weathering sequence. It suggests strong iron leaching as iron 2+, indicative of chemically reduced depletion could have happened under sub-zero temperatures. And I take the iron distribution on a global scale using the gamma ray spectral iron abundance. Each pixel is 5 degrees, and I use the molar elevation to get the average elevation for each beam, and we also give age for each beam, the early Noachian, middle Noachian, late Noachian, or the Noachian parent transition. So basically, we assign the most areally dominant, at least half of the beam, apparent relative surface age for each beam. And then this is the result for the iron abundance changing with time. We already know iron, the early Noachian surface, the Noachian surface is depleted in iron, but the Hesperian surface is really enriched in iron. And we divided them into several epochs. We can see the iron in all of these epochs are below the global average, and the concentration increased gradually with time. And the iron abundance is very high at the surface of the Noachian Hesperian transition epoch. It may suggest a strong oxidizing event, which causes the oxidizing enrichment of iron. Basically, the increase trend is gradual. It suggests an irreversible iron leaching trend, and we also calculate the iron leaching efficiency under each epoch. We can see the iron leaching efficiency in the early Noachian is pretty high, and the efficiency decrease gradually suggests the atmosphere get oxidized gradually from the early Noachian to a late Noachian, and gets suddenly oxidized from reducing to oxidizing under the Noachian Hesperian transition. So this is iron abundance changing with time, and then we can see how iron abundance correlates with elevation or latitude. For early and middle Noachian terrains, we can see the iron abundance decrease with increasing elevation. But for the late Noachian and NHT, we can see the iron abundance is laterally related with the latitude, higher latitude, less iron. So basically, we know higher latitude or higher elevation has lower temperature, but their iron abundance is pretty low under such lower temperature conditions. So, it is possible there is more iron depletion. Therefore, less residual iron in rocks in lower temperature regions, whether the low temperature conditions promote more iron depletion at the surface of Mars. Basically, under low temperatures, water can rise to form the water ice, and the residual water can be more acidic owing to the concentration of the hydrogen plus, and the hydrogen plus can attack the minerals to release iron or magnesium. And during the thawing stage, the released iron 2 plus or magnesium can be leached out of the system, and the new fresh acidic water can supplied and make the water acidic again, and another freezing cycle can make the water-rock interaction continuous. Thousands of freezing cycles can lead to abundant release of iron and leach of the iron. Therefore, freeze cycles is a very efficient method to release and leach iron. And lower temperatures, there would be higher degree of freezing and lower pH and more release of iron. Or low temperature can promote longer water-ice-rock interaction, which can release more iron. Therefore, we hypothesize iron leaching degree increase with decreasing temperature. Therefore, the iron abundance could serve as a a good proxy for temperature and phase source cycles temperature range. And then let's see the iron abundance, the correlation between iron abundance with elevation and latitude, and to see how they change with time from early Noachian to NHT. Basically, we can see the correlation efficient between iron abundance and elevation is pretty high on early Noachian Mars or middle Noachian Mars, but the correlation efficient decrease gradually with time. But it increase for latitude. We can see the correlation increase gradually with time, and this is the basic result. So, if iron abundance is an effective proxy for temperature, from this figure we can see temperature was elevation dominant in early and middle epochs, but become more latitude dominant to form the bipolar ice caps with time during the Noachian period. And the trend is gradual, and the trend is comparable with the gradual atmospheric oxidation trend. So basically, we guess Mars has become bipolar on its very early stage during the Noachian period, owing to the decreasing greenhouse caused by the atmospheric oxidation. So for some take-home messages, the iron loss from paleosols is direct geologic evidence for the reducing atmosphere on Mars, and then phase source cycles is an efficient chemical weathering process to leach iron, and lower temperature can promote more iron leaching. And Mars has become bipolar during the Noachian period in its very early stage. And the data are mainly from the CRISM and the GRS, and founded by the work was funded by the Hong Kong UGC and NSFC. And that's all. Thank you very much.
All right, I think we have to move on.
Well,
we can. Yeah, there's time for one quick question, if you.
We're waiting for some questions, but there is no questions. So thank you very much again, and we could hear you and see your screen. Thank you very much.
Right, and to close this session and start actually the session on escape, isotopes, and evolution of Martian atmosphere, we welcome Shannon Curry, who's going to talk about the first detection of atmospheric sputtering, past and present.
Okay, thank you for having me. I'm really excited to be here today. So this is, we're gonna go way high up in altitude here, 200 to 400 kilometers, so bear with me. I'm gonna try and link this to the broader system the best I can. So I wanna start with Martian atmospheric evolution on the huge, huge scale. So I'm the PI of MAVEN, and MAVEN is the Mars Atmosphere and Volatile Evolution Mission. And it's actually the best observer of atmospheric escape anywhere in the solar system right now. And that's both a good and a bad thing. We actually don't have an observer like this even at something like Earth or Venus. And so the physics we're learning from MAVEN about how Mars's atmosphere evolves is this incredible natural laboratory. So one of the things that's come up a lot during this workshop and conference is obliquity. But I want to point out that in addition to obliquity, the early active sun also drove huge and major changes in Mars's climate with that same kind of like veracity that we see when we think about these huge epochs of escape and then flattening out. And so I really like this cartoon here on the right. You can see it's time over just the loss rate. So in present day, we have the escape rate that we're measuring now with all of the physics and the instruments that we can. But you can see way back in time when the UV, while we have a faint young sun paradox, the solar wind was much higher. And that was effectually punctuated by these major solar storms that really spiked up that escape rate. And so we can see as all the way back, especially in the Noachian Hesperian area, that's when the atmospheric escape rate was at its peak, and that's due to a very active early sun. And those are mostly, we understand most of that through models based on our present day escape rates, but we can constrain them through isotope measurements, and so we don't just get carried away. So Maven can observe what I like to say the drivers from above and below. I won't go through our whole instrument suite, but I do want to point out that we can understand both the drivers, things like dust and heating from the surface, as well as understanding the sun. And what Maven was designed to do was to look at all of these inputs and then look at the immediate reaction of the atmosphere, specifically how the atmosphere responds and how it is escaping when all of these drivers are input into the system. And so today we're going to be focusing on the physical escape channels, namely one of them. So we can measure photochemical escape, genes escape, ion escape, and sputtering escape. So just a quick 101 on these processes because they all tie together. So when neutral atmospheric escape, we have genes escape, right? So that's going to be like lighter elements, namely hydrogen. That's going to be particles just from the tail end of a distribution. And with photochemical escape, that's mostly dissociative recombination. And so I just like to do a little bit of a cartoon. It might help. So with genes escape, you can start to see here. There we go. At the cold end, they just move around a little bit. But on the tail end, they can actually escape. And the rough order of magnitude that we're looking at is like 10 to the 26. I'll convert that at the end for you, but this just puts things in scale. And that's going to be things like hydrogen. Photochemical escape. Here, you've got that photon. It breaks up, right, the O2. I'm oversimplifying the process, but through collisions, then all of a sudden, one of those neutrals can actually escape in an excited state. It's energized past the escape velocity, and it can escape. Okay. So now, if we go on to more ion and neutral atmospheric escape, we have ion escape. So that's when neutrals, they lose an electron because they get ionized by the solar wind, and then they can sense electric and magnetic fields and get swept away with that escape velocity. Sputtering is sort of like a solar cannonball. Basically, ions precipitate into the atmosphere and splash out neutrals. So, what does this look like? With ion escape, you've got your photon or something else, but effectively you ionize that particle. And now, all of a sudden, it can sense magnetic fields, and it gyrates around and escapes the system. Sputtering is a little bit like this, and that's around 10 to the 24. Sputtering is like this, but here, that same ion, when it sees that magnetic field, it starts circling around, but this time it crashes into the atmosphere like that, like a cannonball, and splashes out the neutral. So, here, we don't have an escape rate because we have never observed it until now. We know that it exists, and we'll talk about that in a minute, but we just don't have an escape rate. So, again, why do we care so much? Those lighter ions, those cannonballs, they splash into the water, and so, you can think of like throwing a penny in a pond, and you get a few drops out. Heavy ion sputtering is a little bit more like this. Thinking of doing a big animal jumping in a pool. This is what we splash out, and this is why I personally get so excited. This is one of those escape rates that it's really elusive to observe, but really, really exciting if you can. So Bruce Zukowski did a study back in 2017 in Science, and how do we even know sputtering? Do we definitely know what's happening? We do, because of isotopic enhancements, and so fractionation. So when we look at something like argon, so Bruce's paper looked at argon 38 to argon 36 and saw an enhancement. That means there's more argon 38, the heavier one, than 36. Hence, the lighter species are getting stripped off preferentially over time. So one might say, okay, why do we know that's sputtering? Why couldn't it be something like hydrodynamic escape? But hydrodynamic escape is like a bowling ball. It's going to take off the whole top of the atmosphere. It wouldn't be quite as efficient at being able to just pick off 36/38. The only way you can get this kind of isotopic fractionation is through sputtering. And this paper actually found that 65% of argon was removed via sputtering. So this is an incredible bookend for us to start with. So one of the other reasons we get so excited about this process is, again, because of the early sun. So this is where I'm going to bring us way, way, way back out from the surface, all the way to the sun, because if you're not a heliophysicist, you may not be aware that in today, our sun's actually pretty quiet, even though, we still see we're in the peak of our solar cycle. The thing is, billions of years ago, the sun was spinning faster, and as it was spinning faster, those magnetic fields got wrapped up and it was more active. That means there are more solar storms, and these solar storms are like hurricanes. If you think about like a seashore, right, just slowly being eroded away with the waves are lapping at it, this is like a hurricane coming through and just really, really, really just doing an incredible amount of erosion. And so this is what the solar storms do to the top of the Martian atmosphere. And so back in time, we think that sputtering actually could have been the dominant escape process. So how do we measure sputtering? It's very elusive, and there's a reason that we've now been in orbit 11 years. It's been 12 years since launch, and we're just starting to see it. And that's because the first thing is where these solar cannonballs happen, they can actually happen anywhere on the planet. So we have to have a new mapping system. If you don't like plasma, which is, first of all, probably a lot of the room, and second of all, you can ignore the rest of this. Just note that we're going to now start to call, can't see it, but at the top there, it's called the -E hemisphere. That's just where this electric field points down into the planet, and that's actually what drives all of those particles in. So the precipitation, those are these like cannonballs that are coming in and splashing things out. So one thing to note is that oxygen, hydrogen and carbon are really reactive. So we have been looking for sputtering in those species, but that's not plausible, or not possible, because we can't resolve it from from the photochemical component. So you've got hot oxygen and hot oxygen. How do you tell which one is which? We can't right now. So we chose argon. Argon is obviously a noble gas, it's inert, so it's this beautiful marker we can follow, where if you see argon in different places in the altitude, that's when you can start to see something got it there. So the first thing is we started looking at argon. The second thing, if you look at this plot on the left, these are all the components of argon, and it's a function of density versus altitude. And the thing to note here is that sputtering is only dominant. The black line is the total, and the blue line is the sputtered component. It's only dominant over 350 kilometers. I will not belabor this with why that's observationally hard to do at that altitude, but it is. And so the first challenge was, okay, first it's argon. Second, it's got to be at high altitudes. And then third, the model simulations, these are from François Leblanc and Ronan Modello. And when we did this EGM, this exospheric simulation, we found that sputtering is it's most visible on the night side. So we need argon, we need it at high altitudes, and we need it on the night side. Okay, so this is what we did. It took 9 years of data. That top panel is the solar wind. We have to measure that so we know where all the precipitation is happening. That middle panel is the spacecraft, day side or night side. So it took us almost 10 years to get enough data on the night side to be able to do this study. And this was something I would run every year to see if we had the data, but we didn't. Then finally, on the bottom panel, you're looking at that high altitude argon. So the results. What we're seeing here on the left, at lower altitudes, when you divide that -E, the enhancements of argon, where you would expect to see all that precipitation, like those solar cannonballs, to where you wouldn't, you don't see anything at lower altitudes. Here you can see, on that left, you can see a reasonably flat line, because we're taking the ratio of the two. On the right, however, here at the higher altitude, you can see that enhancement, and that's actually a log scale. So we saw a huge enhancement at higher altitudes in argon. And again, argon, an inert noble gas, we're seeing an enhancement with the solar electric field. And there's only one way to explain this, and that's through sputtering. So finally, we actually caught sputtering in the act, which we were very excited about. This is a case study. So this is a solar storm. This is a coronal mass ejection that went past the planet. Let's see if I can hit that again. There you go. You can see that storm going right past Mars. And so solar storms, one reason I love solar storms for many reasons, one of the top 6 easily, is that it provides a glimpse of what the early sun might have looked like during its constant active and stormy conditions. So we saw this CME, and we saw the argon now go up in the densities go up by an order of magnitude. And here, what you're looking at is time. And on that top panel, that's the pressure of the solar wind, like that's the pressure of the storm. The second panel is actually seeing where the electric field's pointing. It's in the -E hemisphere, and we're in the northern hemisphere. So that's basically, we're in the exact right place at the right time. And then on the bottom panel, that's that beautiful argon enhancement. Again, lofting argon like this can only really be done in one way. So we were really, really excited by this. So I will just point out, when we went and compared to the predictions of this using the LeBlanc and the LeBlanc models, we actually found that the escape rates we were seeing were about 4 times higher than previous predictions, and that's present day. That's a big deal, because if we think that we're off by half an order of magnitude almost, that's a big difference in how much atmosphere has escaped over time, because we know this is the low bookend. We know that sputtering was most likely the dominant mechanism, and we're now in the process of trying to find observationally some more ways to study this. But if this is actually true, then it was the most intense atmospheric escape pathway. So if we just tie this into, the past of Mars, we're now starting to. This is just adapted from a Chassé figure back in 2007. But we're now trying to work in different epochs of what these escape rates would look like over time. And we currently think, using these estimates, that Mars has lost, with this escape rate, 800 millibars of atmosphere, or that would around be 23 meters, like a gel, 23 meters of water globally. So we're still working on this problem and trying to punctuate it over time. So I will just end there and just say it took well over almost 10 years of observations to find this. This is a major, major finding for us, just to understand the physics of escape, so we can start to really think about what was happening so cataclysmically back in time, especially during that Noachian and Hesperian era. Excuse me. And we also found, again, that the argon escape rates are 4.5 times higher than previously modeled predictions. So this is really important to understand for quiet conditions and stormy solar conditions, and we're going to continue working this problem back in time. Thank you.
We have time for questions.
Thank you, Shannon. I'll just make a comment. Thank you so much for a very basic and very convincing story about how all this works. It really helped a lot of us understand, and this is great news and very interesting recent results. Thanks.
In fact, I have a question now that in the review papers, for instance, by Bruce in 2018, that at the end there is a kind of estimation and there is a table and there is a result, I think, by Janet Luhmann about an escape up to 7 bars of CO2 by sputtering. Maybe I'm wrong. And I was wondering, maybe it's a question for Leblanc, I don't know, or Bruce, is the Janet Luhmann, compared to the Leblanc et al. Model that you mentioned with the factor of 4, do you think it's in line with the Luhmann model, or it's below, or it's just to estimate, know that what means in terms of millibars, bars, or?
Jan, that's why I did this study, yes. So the Luhmann study, I would say it's completely in line with this. So François Leblanc and Janet and I worked on this for a long time. The numbers she came up with back in the 90s in her modeled predictions are at the peak of, so like at the billion-year mark. And so we think that, yes, that not 70, did I hear 70 bars? That's... No, Oh, 7. I was like, that seems high, like Venusian high. Yeah, so 7 bars I think is on the very, very high side. But we would see that, I mean, I think, I'll just say it since we're in a friendly audience, I think it's very possible that sputtering drove at least half of the atmospheric escape that we saw today from some of these initial model results.
Okay.
So that would be in line
I understand
with
it's a little early to integrate in time, but my question was, if we compare the Luhmann model to the Leblanc model, the Luhmann model applied today, is it
it's higher.
High in it's assuming
It's about 30%.
Higher? Okay.
It's about 30% higher, but that was just partly based on the computational facilities they had in the 90s.
The same order of magnitude, no? Okay.
Like 10 processors, whereas François now uses, thousands, if not millions. So.
I do have a quick rookie question. What's the mass sensitivity of sputtering escape?
The mass density?
Mass sensitivity. How does it escape much more hydrogen than carbon, or is there?
Do you mean like the efficiency of how things escape, like
Yeah,
the yields are?
Yeah, how sensitive is it to the mass of the element?
Very.
Okay.
Yeah, and the two big things that really determine, again, that cannonball are going to be the mass of that incoming particle and then what's being ejected, and then also the incident angle. The incident angle, if it comes in at the right angle with a certain mass, that's when you can start to see the highest yield. So those are the two biggest factors, but very sensitive. Yeah.
There's no other question. I think François has an announcement.
Hi, I have 2 announcements. The first one is to say that there are still some seats available for the dinner tomorrow evening. So if you want to bring someone or you want to invite a colleague, just talk to me and we'll see. So it will be nice. And the second announcement is that we have some time for the last session, so let's resume at 4:10. So in 35 minutes. Thank you. Let's have a break.
Welcome back, everyone. We're going to keep going with our escape, isotope, and evolution of Martian atmosphere session with next talk by Renyu Hu from JPL on the CO2 and 2H2 atmosphere and transient habitability of ancient Mars.
All right, good afternoon. First, I would like to thank the organizers for bringing us all together here and giving me the opportunity to talk. It's really I think it's really the conference I look forward to the whole year because I've been myself been focusing a bit more on exoplanets with JWST in the recent years, but really this atmosphere evolution of Mars is a project dearest to my heart, and because it's so interdisciplinary, and we can bring together atmosphere science to geology, geochemistry, and today I will present to you a synthesis of what we learn, and particularly from the lens of these isotopes. But really, just hearing all the talks that happens in the past 2 days is truly illuminating, and I think this interdisciplinary spirit of the meeting is just shining through. So I think that
I don't need to repeat any of these things on the plot, but we have many different lines of evidence that also a variety of aqueous activities has happened on the surface of Mars when the planet was young. And one aspect of Notion, for those people who are, just coming into the field, is that not only we know that there has to be some liquid water on the surface for some period of time, the exploration for the past decade or so has also tell us that the liquid water cannot be, too much. It's probably unlikely to be a global ocean for over, a big part of a billion year, and there's the lifetime and the availability, the horizontal expand and the lifetime of those liquid water environments has to be quite limited, and that actually give us constraints on what kind of climate that we should aim for, right? Obviously, it cannot be too cold. It cannot be as cold and arid as today's Mars, but it actually cannot be like Earth, right? It cannot be a true warm and wet system based on the current geological evidence that we have. So, based on this, I think that any work to think about what kind of atmospheres that will give rise to the needed climate, we have to start by thinking about the atmospheric pressure and composition, because that's basically the parameter that you can put in any climate models. The direct measurements of the atmospheric pressure is actually quite hard. I'm showing some examples here. You can do that through certain morphological features and through some inference. Then you can put some lower or upper limits, and it's pretty wide lower and upper limits, as you can imagine, for the surface pressure when the planet was young. And the other question about, we suppose that the early Mars had a much massier atmosphere. Then what happened to this atmosphere, how Mars has lost its early atmosphere and then become a very thin atmosphere today. So I think these two questions can be approached by bringing together these isotopic compositions as the fingerprints of the atmospheric evolution. So we now have these very precise measurements made by Curiosity. So I make a compilation of those data here. And those measurements covers hydrogen, carbon, nitrogen, and argon. I would like to point out here that, for the D2H ratio, the hydrogen, the different water reservoirs on the surface of Mars could have vastly different D2H ratio, as shown by data and models. So, D2H is actually fairly complicated, but for carbon, nitrogen, and argon, there is actually there is no evidence to suggest that the different reservoirs of those elements would have different isotopic signatures. So we can, for the purpose of understanding atmospheric evolution, I think we can just treat them as a single reservoir, which greatly simplify our interpretation. And these different gases, these different isotopic pairs actually show you in a moment that they trace the strengths of different processes that would impact your atmospheric evolution. So by bringing these elements together, then we can start to trace back what has happened in the Martian history. Another piece of sort of evidence that is quite important is MAVEN measurements. Shannon just gave a fantastic talk going over the key known thermal escape processes and how MAVEN has made definitive measurements. I would like to point out the things I found particularly impressive in the MAVEN measurements, which is the constraining the extent of this distance from the homopause when the atmosphere is well mixed and the axial base where the escape happens. The distance, the vertical extent of that space really tells you how much isotopic fractionation it would happen for carbon, nitrogen, and argon as these elements diffuse from the homopause to the exobase and escape there. So that's a direct, for the first time, a direct measurements by our space mission. And also, MAVEN has measured the relative sort of escape rate. We just heard about the sputtering rate, but also has measured the escape rate in other processes. So bringing these isotopic measurements and the the escape measurements together, as well as taking into account the mineral records that we have gathered in the past like 20 years, including the carbonates, nitrates discoveries and measurements. We, in the past several years, has designed this new model of planetary evolution that covers the water, nitrogen, CO2, and argon, and we take into account key processes as the production of those gases from volcanic outgassing, and then the removal of those gases through both thermal and non-thermal escape, as well as the deposition into the crust through the weathering process. So, and each of these processes, we try to model them, and then add necessary parameterization. So you might think that, okay, there are so many processes in play, and how we can constrain anything given we have just a couple of data points. So there are several things here. So we designed the model so that it can be run very fast. So we can run a large ensemble of models, like 10 million models, and we can not a single model will. The data does not tell us that there's a single pathway that mass has to go through, but the data does tell us there's an ensemble of these models that will provide us the correct isotopic ratio at the present day and the correct partial pressure of these gases. So this ensemble of models points to a range of early mass conditions that we can work with. And a second thing I want to point out here is that there are actually common themes in many of those processes. For example, the sputtering, just the process Shannon just mentioned, it actually is produced by the precipitating ion, right? And that ion sputter the atmosphere and then yields escaping nitrogen, carbon, and argon. So the escape rate is basically the precipitating ion rate plus the yield rate. And then the precipitating ion rate is a same rate for nitrogen, carbon, and argon. It's the only different thing is the yield. And the relative yield is relatively well known. So by putting together all of these elements together, so we have multiple angles of evidence, but they have to be following the same underlying sputtering rate. And the same goes for volcanic outgassing, right? Because it's the same volcanic rate, but it will create it will release outgas different gases according to their concentration in the magma. So in terms of the isotopic effects, the most important isotopic fractionation effect is the photochemical escape. So the sputtering might be the process that removes most of the mass from the atmosphere. Its fractionation is somewhat limited because the escape process itself is not fractionated, it's very energetic. The fractionation comes from the diffusion from the homopause to the exobase that MAVEN just measured. The photochemical escape instead, by itself, is strongly fractionating. So in this work, we have re-evaluating the photochemical escape of carbon and nitrogen and the isotopic fractionation in it. Physically it's very simple. You dissociate your molecules, and the excess energy is deposited into the resulting fragments according to conservation of energy and the conservation of momentum. And because different fragments will have different mass, especially when taking into account isotopes, the escape probability from from each photon coming in would be slightly different. So you can take into account the solar spectrum, and then you can derive what would be the photochemical isotope effect here. And the number in the blue is actually the fractionation factor. For those who are familiar with isotopes, you can realize that those are very, very substantial numbers. This is not 0.7 per mil. This is 0.7, right? This is a huge number in the isotope world. So it's very efficient in making the isotopic fractionation. So just want to give you an example of how we apply this model. So for nitrogen, which is the first elements that show strong evidence for atmospheric escape, this is the Viking data early on. And even in the Viking days, people have already quite realized almost immediately that when you include this isotopic effects of the photochemical escape of nitrogen, you already got too much fractionation in the outcome. So if you do not include any other processes, you will get nitrogen 15 as much more than what has been measured by Viking. And this is still true with the curiosity measurements. So a number of ideas has been put forward to temper this isotopic fractionation effects, including the nitrate formation, massive absorption in the regulus, or if you have a huge amount of CO2 at the beginning, then relatively speaking, the nitrogen escape will be less. Or, as several authors has incurred, you can have late-stage outgassing, but the late-stage outgassing has to be constrained by our records of volcanism. So we can evaluate the efficacy of each of those processes in our framework, taking into account the current understanding, for example, how much nitrate we'd expect on Mars and how much CO2 that could be given the carbonate constraints. So we have reworked the nitrogen evolution, and in our model, we actually found out that you actually have like 2 different families of nitrogen evolution, depending on where you start with. So if you start with a not so much amount of nitrogen, we found that the partial pressure of nitrogen quickly drops from the fairly high value to the steady state. And then it will basically continue as the steady state where the escape is balanced by outgassing. But when you have pretty large amount of nitrogen, say about 100 to 200 millibar, then it will never reach that steady state, so it will be in a dynamic regime. So the difference here is actually fairly substantial, because in the steady state, your outcome is basically controlled by the relative strength of this process, and your isotopic fraction, your isotopic composition of the nitrogen is controlled by the relative strength between the sputtering and the photochemical escape, whereas in the dynamical track, your isotopic composition will be controlled by the cumulative effect of this process. So talking about the ensemble of solutions that we found, so this is a model that we published that has included carbon, nitrogen, and argon constraints, and these are the ensemble of solutions that provides the correct partial pressure and the isotopic composition of these elements. So I would like to draw your attention to several features in this evolution story. This part is how argon gets the present date isotopic composition. So in our model, it actually, most things happens early on. This is due to the sputtering. And because for argon, sputtering is the only removal process, this isotopic fractionation basically constrains how much sputtering that could happen for the gas, and then by extension to other gases. And the same sputtering should be able to raise the nitrogen delta 15N value to pretty high, and then we have to have some process to bring it back to the present day value. So actually in our model, there is a period on Mars where the delta 15N value are fairly high in between the evolution, and there has to be some amount of volcanic outgassing to eventually bring that nitrogen isotopic ratio down to the present day value. And then because we have to have some amount of volcanic outgassing, which is, by the way, very consistent with the mapping of volcanic province on the surface, that volcanic rate would also create outgassing of CO2. And we know that there's actually not much loss of CO2 for the past 2 billion years, for example. Then that means that the CO2 content in the magma has to be quite small. And in our case, we think that our model suggests that it should be less than the oxygen efficacy less than IW. And lastly, because there is very little thing that can happen for carbon in the past like 2 billion years, most of the carbon's isotopic evolution has to happen quite early on. And this balance between the rise of the delta 13C caused by sputtering has led us to indicate that most of the carbonate form has to form in a relatively in an open water systems where the fractionation factor of the carbonate formation cannot be too large. So what does all of this tell us, in terms of the atmosphere size and composition? So this is the summary of the previous plot in terms of the partial pressure of CO2, nitrogen, and argon, and the total atmospheric pressure. So the CO2 partial pressure is basically controlled by our model parameter, which is the carbonate deposition rate for the whole time. Well, this result is not completely trivial. This result says that in our simulation, in our ensemble of simulations, the carbonate deposition is the dominant carbon removal process. And at least for the past 3.8 billion years, our ensemble solutions does not suggest that the escape and other processes has a great contribution in terms of the mass. The other interesting finding in this is that in all of our solutions, we have some substantial amount of nitrogen at 3.8 billion years before present. And this amount is ranged between like a few hundred up to 100 to 400 millibar. Its medium is around 200 millibar. So this is a fairly substantial amount of nitrogen. And I found that to be a quite exciting result. Early Mars, in addition to the CO2 that everybody assume, and the hydrogen we have heard about at this meeting, that early Mars atmosphere could have quite some substantial amount of nitrogen. So in the spirit of minutes time, I would like to move on to just talk a little bit about the hydrogen aspects. So for hydrogen, there is also quite an over-enrichment problem, particularly if we want to just lose that hydrogen, a few more than 100 GeL worth of hydrogen from the early Mars to now through atmosphere escape. And in this plot, I compare the mantle value, the current value, and what if all of the escape come from removing hundreds of GeL worth of water through the hydrogen escape into space. And that will create a massive over-enrichment problem. And recently, we published a paper that provides a solution for this problem, which is most of the Mars water could just be lost into crustal hydration. And this actually helps us to explain the moderate D2H increase in the history. And it's also quite consistent with the atmosphere escape rate of hydrogen. From the theoretical aspect, we actually do not expect that the hydrogen loss rate to be very high at early time because it is limited by diffusion. So this new picture will allow a few hundred GeL water to be on the early Mars and then to be lost into the crust. And in addition to this water loss story, at the same time as this crustal hydration happened, if you split your water into H and OH and incorporate the OH into your mineral, the free H would get released into the atmosphere. And then that H produced in the crustal hydration, we found that if we average it over the whole Noachian, this won't matter too much in terms of this won't build up too much in the atmospheric, in terms of atmospheric H2 mixing ratio. But if we do not average it over the whole period of Noachian, but let's say 10% of the Noachian, like 40 million years, this could result in the buildup of the atmospheric hydrogen to about 5%, and this actually has a great ramification for the early climate. And recently we did a study that published by Danica Adams last year. We studied the lifetime of this hydrogen and how much time you need to build up this nitrogen, to build up this hydrogen through crustal hydration, or when this crustal hydration stops, how much time this hydrogen will stay in your atmosphere. And we got a time scale of roughly 10 to the 6 to 10 to the 7 years. And that's a fairly consistent time scale as we have heard about for many of the aqueous processes on early Mars. So just to summarize, from the isotopic constraints, we have a range of the CO2 approximately a bar, but it's a pretty large range. But importantly, we think that early Mars should have a fairly substantial amount of nitrogen, which could be a part of your climate story, and occasionally up to a few % of hydrogen. And just in terms of 1D, mean surface temperature as we calculated, this additional hydrogen and nitrogen could, together with about 0.9 bar of CO2, could raise your mean surface temperature to about 260 K, and that seems to be fairly consistent with what you need to sustain some seasonal melting in certain locations. So I leave the conclusion here, and thank you very much for your attention.
Thank you. Do we have time for questions? You can come forward to the microphone. We'll decide. I actually have 1.5 bar of CO2, 0.5 bar N2, 10% of hydrogen. With that level of reducing atmosphere, could we expect like the formation of atmospheric aerosol, who would tend to cool down the atmosphere? You go the opposite way of what you're saying regarding the warming of the G2H2. Like, did you incorporate this in your model? What was your opinion on this?
Yeah, so we in the recent study we published last year, we did a full photochemical model that includes the CO2, N2, and hydrogen. We did find that there could be some buildup, some conversion of CO2 to CO. But we found very, very little conversion all the way to methane. So I don't think that this hydrogen would cause substantial formation of hydrocarbon aerosols.
Thank you. Are there any other questions in the room? Now we can thanks again our speaker.
Thanks.
And so our next paper is by Juan Alde and will be presented by Franck Momessin on the TGO ACS measurement of isotopic composition of hydrogen, oxygen, and carbon.
Thanks. So I will do this presentation on behalf of Juana, who could not come today, but I will try to be as faithful as possible to his work because he led this study from A to Z. And I think I have no need to tell you why it's important to study isotopes and isotopic ratios. If you are not aware of this, it's because you didn't hear the last presentation, which is not good. But today, the point is not so much to explore the implication on the long term, it's rather to see how the current present-day processes can shape the isotopic ratio as we observe them. And you have here sort of an illustration of our point, that is what we observed in the lower atmosphere turn into something else when it comes to the upper atmosphere where they can escape. So there is some kind of a dichotomy which can be related to the fact that there are some processes acting in the lower atmosphere or in the middle atmosphere, which changed the perspective on the isotopic ratio. And for this, Juan has used one of the spectrometer on board the TRACE orbiter. It's an infrared spectrometer, which covers a wavelength range where there are many species that we can detect because they have spectral signature embedded in the spectra, namely water vapor, CO2, their isotope, name it. But his work has focused mostly on CO2 and on H2O, you will see. What's good with this instrument and this mission is that you can probe the Martian atmosphere leveraging the fact that you have larger air mass and larger number of molecules that you will probe with your instruments, and therefore higher sensitivity to detect the gases you're looking for. And you also rely on a very high signal-to-noise ratio because the sun is the brightest thing you can find in the sky. And we use all the photons from the sun to probe the Martian atmosphere. The other thing that is not listed here, which is also very important, is that we have the spectral resolution, which allows us separating the different isotopes in the spectra. And you see here an example for CO2 where the various oxygen isotopes, carbon isotopes are represented and can be observed and cleanly separated in the spectra. So we have signatures for each of these elements that we can actually use to retrieve their quantity, obviously. We can do the same with water vapor here. So we have an example of a spectra which has been collected. We have a model which we try to reproduce these tiny features when they are present, especially for HGO, which might appear a little less visible than other features, but it's there and we can retrieve this. And so the goal is then to tell something about their altitude distribution and see how this altitude distribution is, let's say, diverting from what could be a uniform ratio, telling that something is happening, creating some fractionation process that we can characterize. So let's start with water vapor. So water vapor has been observed for a long time now. We have several years of compilation of data coming from the instrument. We can probe basically the water vapor from roughly 5 kilometers up to 60, 70, 80 kilometers, depending on how much water vapor we have in the atmosphere and depending how high it can go. And you have here an example of a survey which has been performed for 2.5 years, from Martian year 34 to Martian year 36. You see here data which have been collected by one of the other channel of the SES instrument, which has been used by Azana Fedorova, who produced these water vapor mixing ratios for the two hemispheres. And what is striking in this plot is that you see that there is a strong dichotomy between the northern spring and summer and the southern spring and summer, where actually water vapor can, I don't know if I can use the laser or, but it's okay if I can't.
You can firstly move your mouse if you want.
Okay.
But we can change it into a lighter.
Okay.
But I think this is good.
Okay, that's fine. Okay, thank you. So yeah, you see the, well, a little sensitive. You see this very strong dichotomy. That's because water vapor during southern spring and summer can reach very high altitude. The atmosphere of Mars is more dusty. There are more storms, which put a larger amount of dust in the atmosphere. It's closer to the sun. Temperature is rising. So there is no condensation or cloud formation which impedes the transport of water vapor to high altitude. And so you see the drastic changes between typical profile that you can see on the right on the plot is more, let's say it's more obvious here that there is a very different behavior of water vapor between these two seasons. We can actually see the same with the overage thanks to combining the isotopic lines of water vapor. And we are actually seeing something which resembles the behavior which correlates with the water vapor. Basically, we see a decline of the D over H, that is of the HDO on H2O, at an altitude where water vapor is already declining. And that's because something happened that is well known by modelers, and that is the fractionation at condensation. So basically, when a cloud is forming, the HDO is concentrating in the ice phase and is depleting the gas phase from the heavier isotope. So that's why when a cloud is forming, there are less HDO relatively to H2O in the atmosphere, in the gas phase. And that's important because that means we will concentrate the HDO anytime we have a cloud that is forming, and if the water vapor wants to propagate higher, it will be depleted in HDO, and that has obvious implications for the escape at much higher altitude. So we have these two situations basically where aphelion and perihelion are the two main seasons worth of studying. And you see that the overage is actually declining at much higher altitude when during perihelion. That's expected based on the fact that the climate of Mars at this time is much warmer, much more intense in transport as well. The thing that I would like to draw your attention to is that when you try to represent all the processes which is involved in the fractionation process, in the cloud formation in particular, we have great sensitivity to some particular microphysical aspects which can completely change the picture. And actually, if you don't allow supersaturation to happen, if you force water vapor to condense whenever there is an excess of saturation, you will block water vapor much more efficiently, but at the same time, you will reduce the D over H at the altitude where the cloud is forming. And that has strong implication on the propagation higher up for D and H, obviously. And that tells us that we need to be very delicate in the way we represent the microphysical processes involved in the cloud formation. Let's go to carbon dioxide. Yeah, for carbon dioxide, the story is a little more, let's say, easier to understand. There, the question is how both isotopes C13O2 and 12CO2 are propagating upward. And we see that there is a deviation at higher altitude. And we see this decline, which actually is the result of the diffusive separation of the two isotopes. One is heavier because at higher altitude, the turbulent mixing or the overall mixing of the atmosphere is no longer dominant. Then comes the time of the molecular diffusion at higher altitude, and we see actually a decline which is very much in line with what you expect based on the molecular mass and the diffusion of these two molecules separately. And therefore, we are actually confirming here that what shapes the profile of C13 and 12 and C12 at higher altitude is molecular diffusion. The last exploration regards carbon monoxide. And here the story is also quite fascinating. So we have here profiles showing many data compiled together from which we were able to statistically derive a profile for O18 over 16O, C13 over C12. And that's coming only from CO. We compare it with the value that has been observed by Curiosity, and you can see that there is a very strong difference between the C13 ratio of Curiosity and the one that we observe with CO with SES and the trace gas orbiter. There is a clear deviation. And to interpret this, we need to invoke another type of fractionation which occurs now during photodissociation. So when the UV light is actually separating the CO molecule something happens. And what happens is actually that 13 CO is more preserved than 12 CO from photodissociation. So when CO is forming, actually, it is less. It has less. It has a fraction of C13, which is smaller than in its parent molecule, which is CO2. And so that's how we go from, let's say, relatively rich C13 in the CO2 into a rather poor C13 in CO. And that explains that can be actually reproduced by a 1D model. You let the model run for 20 today in terms of isotopic ratios for these molecules is mainly controlled by present-day processes. So this is very contemporary when it comes to explaining the profile that we see and perhaps sometimes even the bulk. So after 5-6 years of exploration, the ACS and trace case orbiter have been able to deliver, I think, a very neat exploration of the isotopic ratio of C, O, and H. It has essentially confirmed things that we were anticipating, actually the role of condensation, the role of diffusive separation, and the role of photochemical reactions, but it's actually now confirmed by the observation, and that's one of the roles of actually our instrument around Mars is to see things that we were expecting and to see things that we were not expecting. Thank you.
Thank you, Frank. Questions in the room?
Bruce Tchaikovsky, University of Colorado. I want to ask you about your opinion on something, since I don't think the data will tell us, and that is D2H in the polar ice that is the source for summertime pulse of water into the northern hemisphere atmosphere. Do you think the D2H is uniform within the ice? How much do you think it varies?
That's my favorite question on the average. And that's the only I can actually answer, really. Why? Because it's so history dependent that it's really hard to tell. And we have one of the experts here sitting, which has been working on, and who knows more than me about the layering processes in the overage. There is layering for sure. I mean, we cannot assume that the entire polar cap is at equilibrium with the atmosphere. It's not possible. It's not physically possible. So it's basically history dependent. And if it's history dependent, then the climate, the temperature, the amount of water vapor, the cloud formation will eventually create this layering and potentially hide more deuterium than there actually is in the atmosphere. So you see, I have no way to really precisely answer your question, but I am pretty sure that what there is now in the polar cap in terms of isotopic ratio between DH is not the one that we are seeing in the atmosphere, for sure.
There's no other question. We can thank Frank again. And our next and final talk of the session will be given by Dee Wang on the comparative analysis of water isotope between Earth and
Good afternoon, everyone. My name is Wang Di. Thanks for being able to present our work on comparing tropospheric water vapor isotopic distribution and control than Earth and Mars. I will repeat same part of background already introduced in previous two talk, that early Mars, like Earth, likely had liquid water, but now it's a frozen world. Previous study based on the fact that D2H ratio on Mars is about 5 to 7 times higher than on Earth, conclude that Mars had lost a large amount of water. That's mainly because the lighter hydrogen can escape more easily into the space, but this occurs in the upper atmosphere. Before that, the tropospheric process may already influence the baselines that will influence our estimate of the water loss on Mars. So here we want to focus on the troposphere. We questioned what controls the tropospheric water isotope behavior on Mars and Earth, and what's the similarities and the difference. So on Earth, we used the draw to measure the vertical profile of the vapor isotope up to the upper atmosphere. That's a black line, generally predicted by the Rayleigh curve, the red line. As air raise and cools, more vapor condense, so the heavy isotope will condense first. Then the vapor will become drier and lighter. Just follow the Rayleigh curve, the red line. It depends on temperature. So we can see that the observations align this Rayleigh curve when the humidity is high in the low altitude. Then it lie above the Rayleigh curve. It's likely due to ice sublimation, because when the heavy isotope will condense first, so the ice crystal is reached in heavy isotope. So when it sublimates, it will release heavy isotope back into the vapor. So it will enrich the surrounding vapor. To test this, we add different contribution ratio from ice submersion to the Rayleigh curve. From the red to blue, the contribution ratio increase. So the observations shift toward to the blue line. That suggests that ice submersion to the contribution of ice submersion to the vapor become stronger higher up. To study if this process also occurs on Mars, we used LMDZ for Earth and PCM for Mars. On Earth, the vapor mainly comes from the low-latitude ocean evaporation. On Mars, it mainly comes from the submersion in the polar region. So we took 2 vertical profiles. It includes the ascending region in Hadley circulation and polar region, and also the May vapor source region. We can see that the simulations, the dot points, consistently lying above the Rayleigh curve. It indicates that ice submersion elevates D2H on both planets, and with a stronger effect on Mars because the longer lifetime of ice crystal, larger temperature swings, and lower pressure. Then we look at the longitude transect. Here we show 2 layers near the surface and near the cloud top. Near the cloud top, the ice submersion effect become most pronounced. Also improve that ice submersion is a key driver of the isotope variation in the upper atmosphere. Then we look at the impact of storm. During the typhoon event on Earth, the D2H ratios decrease compared to pre-storm period, shows negative values in their difference. It's because convection results in heavy rainfall. So follow the Rayleigh process, heavy isotope condense, then the vapor become lighter and lighter. And besides, the partial rain evaporation further decreases. Rain crystal is solid, so the isotope cannot react very fast, so it will directly sublimate. So the heavy isotope sublimate directly, then it will enrich the surrounding vapor. But rain evaporation, if just partial rain evaporation in the surface, the lighter isotope will diffuse faster, so it will depleting the surrounding vapor. On Mars, the D2H ratio in global dust storm year is much higher than a common year, shows positive values in their difference. It's because that dust storm lift heavy vapor to higher altitude, and the high dust and warm air result in less condensation, so the heavy isotope can remain in the vapor. And because of no liquid and Mars, so no raindrop evaporation. So this process will enrich the surrounding vapor. In addition, the ice sublimation effect also becomes stronger during storm. In MY34, the dust storm started around 185. The D2H repeatedly increased and spread to higher altitude. That's also because dust lofted the ice to higher altitude. This ice carries heavy isotope, so their sublimation result in a stronger D2H increase in the vapor. This video shows how the the evolution of D2H during storm. On Earth, during the continuous convective events, D2H ratios shows varying degree of decrease, transport from the tropical region to and north forward. It's related to the convective strength. And Mars, I will show the. And Mars, when the storm starts, the D2H ratios increase and repeatedly spread to high altitude and high longitude by Hadley circulation. So storm cause opposite isotope response, depletion on Earth and enrichment on Mars. So far, we mainly analyze the variation under the equilibrium process in the equilibrium conditions, like condensation or ice submersion. But when this phase change occur under non-equilibrium conditions, the kinetic effect will become important, because the non-equilibrium condition, like very dry or supersaturated conditions, the kinetic effect will become important. The lighter H2O molecules will diffuse faster than HDO. This process will slow the depletion of the vapor and enrich the D2H. So in the North summer, it's very dry in the south, but in the meantime, you can see that it's supersaturated in the south. That result in significant increase in D2H in the south polar. It drives up to 50% of D2H enrichment of the atmospheric range 3 of 6. It's similar in the south summer. It's super dry in the north, but supersaturated in the north. It also drives up to 50% of D2H enrichment. But this is relatively minor on Earth, because supersaturated conditions is very common on Mars, but the difference from the equilibrium remain modest on Earth. So to sum up, the ice sublimation elevates D2H and humidifies the atmosphere on Earth and Mars, with a stronger effect on Mars and within a unified interpretive framework. So for its implication, we can use the observation to quantify the contribution of ice submersion to the upper atmosphere humidity, which plays a critical role for the global climate feedback. And the storm impact D2H differently. Martian global dust storm enriched and Earth's regional storm depleted. That suggests that we can use water isotope to reconstruct storm history and intensity, especially one of the humans' dream come true to have the ice coin on Mars. And the kinetic effect drives up to 50% of D2H enrichment on Mars, but is relatively minor on Earth. Also, ice submersion, storm, and the kinetic effect can increase the D2H in the atmosphere, in the lower atmosphere, in the troposphere, highlight the lower atmosphere isotope effects that should be taken into account when we estimate the water loss on Mars. Thank you for your attention. I welcome your question and feedback.
Thank you very much. Are there any questions in the room? I have one regarding the effect of dust storm. you very nicely showed the effect of GDS on the D2H ratio. Did you look at how smaller dust storms would affect the D2H? Like, could it be visible with local or regional dust storm? And the second part is, would this be visible in data sets, for example, in TGO data sets?
Here, in my study, I just used the model to do this work, but it's good suggestion to look at the ACS data. And here, this plot shows the global dust storm. Maybe the regional dust storm also have similar influence.
Hey, Eran Vos, NMD. I was wondering if you can elaborate, please, on where does the D2H ratio fractionation, equilibrium fractionation is mostly important, and where is kinetic fractionation is mostly important? Different altitude or different regions in the planet?
Yeah, it's a good idea to see the different impact in different region. And here we just show the influence of kinetic effect. It might be very strong in the polar region because the supersaturated conditions in the polar regions. But it's a good idea to look at, to compare these two effects. Thank you.
Okay, if there's no other questions, we can thank Dee again. And this concludes our sessions with a little bit of time, and we can actually start the poster session now, I think. Yeah. You can see all the nice posters outside. Thank you all the speakers again.